What's up, guys? Welcome back to some linear algebra. So today we're talking finally about dimension. So off the top of your head, everyone has kind of a general idea of what dimension is, but I want to kind of point out, just to start the lecture off, that dimension is sort of a strange thing. If you just have some abstract collection of mathematical objects, right? Some sort of like, okay, here's a bunch of things that have some similar property. When do they have a dimension? That is, when is there some sort of a invariant associated to these objects that is just a specific number, generally a whole number, an integer, right? Positive, greater than or equal to 0 at least, right? That captures the nice properties of what we expect dimension to capture. So it's not always immediately clear that there is such a thing. And I think that while we know that there is, at least for the vector spaces you've probably encountered thus far, it isn't necessarily clear that there should just be a dimension for abstract vector spaces, at least just immediately from the get-go. So what we'll do is we'll build up to the idea of a vector space having this numerical invariant, this integer associated with it called dimension. And the way we'll do it is using some of our tools from last time. So really quick, recall this result from last time. So 2.22, this says that the length of, actually this was two lectures ago. This says that the length of a linearly independent list is less than or equal to the length of a spanning list in a finite dimensional vector space. So in a finite dimensional vector space, the length of every linearly independent list of vectors is less than or equal to the length of every spanning list of vectors. All right, here's the idea. Since a basis is a linearly independent spanning list, this applies. Here's the idea. So, what we'll prove to start off with is that the basis length does not depend on the basis you choose. So that is, if you take any two bases of a finite dimensional vector space, they have the same length. Let's prove it. So let's let v1 through vn and w1 through wm be two bases for a vector space V. By the result above, that is, by this one right here, n is less than or equal to m, since v1 through vn is linearly independent and w1 through wm is a spanning list. Now, notice that W1 through WM is also linearly independent, and V1 through Vn is also a spanning list. Hence, we also have m less than or equal to n. Therefore, m equals n. That is, since both are linearly independent and spanning, you can switch them out in an application of this result right here. So, switch them out. You see that the length of one is less than the other, and the length of the other is less than the first one, and so they have to be equal. Bada boom. Nice. All right. So this gives us what dimension is. The dimension of a finite dimensional vector space is the length of any basis of the vector space. This piece right here this only works because every basis has the same length. So if every basis didn't have the same length, there wouldn't be this, number that doesn't depend on your choice of basis that you could associate. All right. So we'll just denote, so this is just a notation. We'll denote this by dim v instead of writing dimension of v. We'll say dim v. Okay. i.e., dim is a function from the finite dimensional vector spaces to, well, what could the length of a list be? It's an element of the naturals, where here we're taking the naturals to be 0, 1, 2, and so on forever. Yeah? So all of the counting numbers, including 0. I know there's some debate about whether 0 should be a natural number. Just for our notation right here, we'll consider it to be, if you don't want to, then say the naturals union 0. All right, cool. So we've got this invariant associated to a vector space, at least a finite dimensional one, called dimension, and it measures the length of a basis. Let's see what this gives us. So the first thing this gives us is, well, among other things, a lot of obvious facts that we didn't know. That is, a bunch of things that we probably just kind of assumed were true or are used to being true that we have not explicitly shown until, well, right now. So first off, if you have a subspace U of a vector space V, then the dimension of U, I don't want to cover up that less than or equal to part, is less than or equal to the dimension of V. So this is something that seems obvious. Of course, if you have a vector space inside of another vector space, then its dimension can't be any bigger, right? But by itself, it is not necessarily clear that the dimension increases or at least is a decreasing along this less than or the subspace relationship, right? So let's show it. Let U be a subspace of V where V is finite dimensional. Okay. Let U1 through UN be a basis for U, i.e., the dimension of U is n, that's what I'm saying here, and let V1 through Vm, let me put little serifs on there, be a basis for V. Then notice that, well, U1 through UN, it's a basis for U, so it's a linearly independent spanning list. But if U1 through UN, this list right here, is linearly independent in U, and U is a subspace of V, U1 through UN is a linearly independent list in V as well. And V1 through Vm is a spanning list in V. By the result, we recalled at the beginning of lecture what do we know? Well, we've got a linearly independent list in V and a spanning list. The length of any linearly independent list is less than or equal to the length of any spanning list. N is less than or equal to M. That is, dim U, which is N, is less than or equal to M, which is the dimension of V, since this is a basis for V, right? V1 through Vm is a basis for V, means that since all bases have the same length, the dimension of V is m. That is, dimension measures the length of any basis. Okay, cool. So we got that. All right, what about another one? Here, linearly independent list of the right length is a basis. That is a short way to say this one. So we're going to suppose that V is finite dimensional vector space. And what we're going to say is that every linearly independent list of vectors in V of length dem V is a basis of V. So the idea of this is basically that it's not the case only that there are that all bases have the same length. It is the case that any linearly independent list that is the length of a basis is automatically a spanning list. Does that make some sense? Basically, what we're saying is that basis allows you to skip, dimension allows you to skip one of the steps in basis. That is, if you want to show something as a basis, you have to show it's a linearly independent spanning list. But what this result right here is saying is that you can skip showing the fact that it's a spanning list just by showing it has the right length. That is, by using this tool called dimension. Sweet. All right. So here's the idea. If V is finite dimensional, so suppose V is finite dimensional, finite dim, and V1 through Vn is a linearly independent list in V. Suppose further that dim V is equal to n. That is, suppose that this linearly independent list has the length of a basis. All right, basically what we're going to show right here is that it's not the case that some lists of the right length are bases and some of them aren't. Every single linearly independent list of the right length is a basis. Here's the way we do it. So if the dimension of V is n, and this is a linearly independent list, what we do is the following. Recall that any linearly independent list in a finite dimensional vector space can be extended to a basis. This was a result that we proved, I believe, last time. Yeah, it was. So we showed that any linearly independent list can be extended to a basis, but since the length of every basis is the same in a finite dimensional vector space, this extension, terrible handwriting right there, must be trivial. I.e., it must not add anything. Hence, V1 through Vn is already a basis whenever it is linearly independent and dim V equals n. Oh, okay. Basically, all it says, all we get out of this is we know that we can take a linearly independent list, add some stuff, make it into a basis. Nothing too crazy. We did that last time. The whole idea here is that knowing that every basis is exactly the same length, it tells us that if we start with a linearly independent list of the right length, then knowing we can add stuff to get a basis tells us that we don't need to add anything. Okay, it's kind of a silly argument if you look at it like this. It's a really very straightforward proof, but that's kind of the power of basis. Once you've got some sort of simple invariant like this, it gives you a lot of stuff for free. Sweet. Let's do a bit more. Okay, here are two more kind of obvious exercises you can do using this the power of the idea of dimension. That is, having this invariant associated to a vector space lets you do a lot of tricks by just appealing to the fact that it's an invariant. So, first one. Hopefully this is really pretty straightforward. The one after it, I think, is so straightforward that it is almost a duplicate of the one we just did. So the first one will say that, hey, if you've got a finite dimensional vector space, finite dimensional, U, a subspace of V, and suppose that dim U is equal to the dimension of V. What we're going to show is that U is equal to V. Okay, here's the idea. So, if you have a finite dimensional vector space, a subspace of it with the same dimension, what we want to say is that those are actually the same space. That is, that there's no subspaces somehow nestled in between V and, a subspace of lower dimension, except for V itself, right? There's no subspace not equal to V that sits inside of V, right? Some like little vector space inside of V that has the same dimension but is not all of V. Okay, this is maybe kind of obvious seeming in your mind if you are used to working with regular old vectors from the first course in linear algebra, something where every vector is just like a list of numbers. This seems really pretty reasonable, but I claim that if you're just doing it abstractly, hopefully at least, if you think about it for a minute, this maybe doesn't seem totally obvious. That is, maybe without knowing this, without having this thing right here, this doesn't seem like an easy to prove result, or at least without the tool of a dimension. This doesn't feel like an easy to prove result, since there's nothing I can really appeal to say that they're the same. Let's try to do it. So let U1 through UN be a basis for U. Then U1 through UN is a linearly independent list in V, and its length is dim V, since dim U equals dim V. But by the previous result, any linearly independent list of length dim V is a basis. So U1 through UN is a basis for V as well. Semicolon, i.e., U is equal to the span of U1 through UN, which is equal to, well, V as well. That is, U is equal to V. Hey, that's what we wanted. Nice. Okay. Let's do another one. Another kind of obvious fact that we just immediately get out of the idea of dimension. So this one says, suppose V is finite dimensional. What we're going to say is that every spanning list of vectors in V of length dim V is a basis of V. This is basically the same as what we had before, except instead of linear independence, we now have a spanning list. It says exactly the same kind of thing I was getting at before. Dimension lets us get around checking both conditions that we need to check normally to show that something is a basis. That is, you can check either that a list is linearly independent and spans the vector space, or you can just check one of those things and look and make sure that it's the right length. Calculating the length of a list is very easy. This saves us a lot of time and effort, and it's a pretty cool result, having these two things together. So let's start it off. Suppose V is finite dimensional, and let V1 through Vn be a spanning list of length dim v, which we're going to let n equal. That is, what we're trying to say is v1 through vn spans v and has as many elements that in that list as a basis. Okay. Since every spanning list in a finite dimensional vector space can be reduced to a basis v1 through vn can as well, since it is a spanning list in a finite dimensional vector space. But since every basis has the same length, this reduction must be trivial, i.e., we remove nothing. So v1 through vn is already a basis for v. Nice. All right. Basically exactly the same as our proof that any spanning or every linearly independent list of the right length is also a basis. The whole idea of it is to say that you can either extend or reduce the linearly independent or spanning list to a basis, and then because it's the right length, you either have added nothing or taken away nothing, so it must have already been a basis. Nice. Let's get on with it and see if we can do anything more complicated or interesting. Okay, something a bit more interesting. This is the hard one of the day. This one says that if v1 and v2 are subspaces of a finite dimensional vector space, then the dimension of their sum is equal to the sum of their dimensions minus the dimension of their intersection. If you have seen inclusion-exclusion counting before, say in like a discrete mathematics class, this is a direct analogy. So let's prove it. This proof, I will let you know right now, is a little bit of a beast. It is not terribly difficult by itself, but it is kind of long. So I'll try to run through it slowly and not be too terrible about it. So let's start it off. Let v1 and v2 be subspaces of v, a finite dimensional vector space. Let v1 through vn, or actually I'll be careful, m, be a basis for their intersection. Okay, v1 intersect v2. Fair enough. Let me draw like a tiny picture over here. So I've got v1, I've got v2. These guys live inside of v. Okay, now I'll draw like a slightly different color. In this little chunk right here, this is v1 intersect v2. And then, somehow like in the thing containing both of them from their sum, this is v1 plus v2. Basically, you can think of it like this. So the gist of it is that we're going to start with the smallest subspace, fair. That's the littlest shaded region right there, littlest area. Okay, and then we're going to extend to bases of v1 and to bases of a basis of v2. And then we're going to show that you can kind of put those two together to get a basis for v1 plus v2. Nice. Here's the gist of how we're going to do that. So we'll take a basis for v1 intersect v2, the smallest subspace. All right. So that dim v1 intersect v2 is equal to m. Since the length of any basis is exactly the same, and it is equal to the dimension. That's what the dimension is defined to be. Taking this as a basis for v1 intersect v2 tells us that we're assuming the dimension is m, whatever that number is. Okay, cool. What we're going to do is the following. Since v1 through vm is a linearly independent spanning list in v1 intersect v2, it is a linearly independent list in both v1 and v2. So we can extend it in two ways, which are as follows. v1 through vm, and then I will write it as u1 through uj, a basis of v1, and then v1 through vm, and now I'll write it as w1 through wk, a basis of v2. So we're starting out with a basis for this guy right here. And then what we're going to do is we're going to take it in two different directions. One, I'm going to form a, let me make sure that actually looks like the color I want it to. I'm going to take it to do this one right there. And then on the other side, I'm going to take it to become a basis for this chunk. All right, nice. So I've got a basis for v1 and a basis for v2. Then we are saying that dim v1 is equal to m plus j, since that's the length of that list, and dim v2 equals m plus k. This is reasonable. The dimension of a subspace is less than or equal to the dimension of the whole space. So the dimension of the subspace v1 intersect v2 of v1 is less than or equal to the dimension of v1, and so on for v2. That is, the dimension of v1 is equal to the dimension of v1 intersect v2 plus something. Potentially that could be plus 0, but it could be no less than m. All right, fair, cool. Same with v2. So what we want to do we will show that v1 through vm, u1 through uj, w1 through wk, which I will refer to as b, is a basis for v1 plus v2, since this says that, and here's what it says. Here's the argument. Dim v1 plus v2 is equal to, well, how many things are there? There's m from v1 through vm, there's j from u1 through uj, and there's k from w1 through wk. So m plus j plus k, which notice is equal to, I will do the, let me actually do this all in one line just to save some space. This is m plus j, just grouping things together, plus m plus k minus m. That is, if you throw in an extra m and subtract off the m, then you've got exactly what you need. This is the dimension of v1, this is the dimension of v2, and this is the dimension of v1 intersect v2. Basically, it says if you start from a basis for the intersection and you extend it to a basis of each piece giving you the intersection, then you can just take the original list and add each piece of the extension to it to get a basis for the sum. All right. So all we have to do is show that B is a basis for V1 plus V2. Here's the idea of it. To show that it's a basis, we should be careful. To show that it's a basis, we should show that it's a linearly independent spanning list. Okay, fair enough. So notice that B, this list V1 through VM, U1 through UJ, W1 through WK, is contained in V1 union V2, certainly, okay, and is therefore contained in V1 plus V2. That is V1 plus V2. The sum of these two subspaces certainly contains everything in V1 and everything in V2. Okay, so this is in V1 plus V2. Good. The span of B certainly contains both V1 and V2. So it is equal to V1 plus V2. That is, V1 plus V2 is the smallest subspace that contains both V1 and V2. So it is contained in V1 plus V2 and contains V1 plus V2. If you want me to write it out. Okay. Hence, B spans V1 plus V2. It is a spanning list. Now, we need only show linear independence. Okay, we'll continue this on the next page here. So, here, let me jump up here. I'm actually going to move this down very slightly, and then I can finish up the proof up top. So, proof continued. To show linear independence, suppose that we'll need three different sets of coefficients. I will write it this way: A1 V1 plus dot 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 all the way down to AM VM plus B1 U1 plus dot 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 all the way down to B J UJ plus C1 W1 plus dot 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 all the way down to CK WK. Suppose that this thing is equal to 0, the 0 vector, for some A1 through AM, B1 through BJ, W1 through, oh my gosh, so annoying to write all of this in the field. Or not W's there. Ugh, what a fool. Okay, there we go. These are C's. C1 through CK. All of those guys in the field. A lot of different coefficients flying around. There's A's, there's B's, there's C's. Fair enough. Okay. Now, what we're going to need to do is we're going to need to show that all the A's, all the B's, and all the C's are equal to 0. That is the only linear combination of the list V1 through VM, U1 through UJ, W1 through WK. That is the list B, as we've called it. The only linear combination that is equal to 0 is the trivial linear combination, the combination where all the coefficients are equal to 0. Okay. notice that this can be rewritten as the following. I will write it this way: C1 W1 plus dot 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 down to CK WK is equal to minus A1 V1 plus dot 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 all the way down to AM VM plus B1 U1 plus dot 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 all the way down to BJ UJ. And this is minus this whole thing. Okay, so if this is equal to the 0 vector, then you can certainly subtract a chunk of it over to the other side. Nothing too crazy, subtracting off that whole chunk. Okay. Hence, we can see the following. C1 W1 plus dot 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 down to CK WK. This is in V1, since V1 through VM, U1 through UJ is a basis for V1, and this says that C1 W1 through CK WK can be written as a linear combination of those basis elements for V1. Oh, okay. Now, all of W1 through WK belong to V2. Oh, okay. Since, only write this piece of reasoning one more time here. V1 through VM, W1 through WK is a basis for V2. Yeah? Fair enough. Now, what this tells us, so C1 W1 plus dot 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 all the way down to CK WK is in V1 intersect V2. Oh, okay. This is pretty nice. Since V1 through VM is a basis for V1 intersect V2, C1 W1 plus all the way down to CK WK is equal to, one more set of coefficients, D1 V1 plus all the way down to DM VM for some D1 through DM in the field. That is, I've got an element of V1 intersect V2, and I've got a basis for V1 intersect V2, so there are some coefficients such that I can make a linear combination of those basis elements using those coefficients to get that element of the intersection. All right. Now, however, V1 through VM, W1 through WK is linearly independent since it is a basis for V2. So this implies that C1 equals dot 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 all the way down to CK equals D1 all the way down through DM equals 0. And this is just since this thing right here is equal to 0. So taking it, moving it to the other side, look, it says you've got a linear combination that's equal to the 0 vector by linear independence. All the coefficients in that linear combination have to be 0. That's the justification for this piece right here. So we can rewrite this up here as A1 V1 plus dot dot all the way down to AM VM plus B1 U1 plus dot 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 all the way down to BJ? Yeah, BJ UJ equal to 0, since we could take all the C's and set them equal to 0. Hey, how about that? Now, just repeat. For the, even easier, for the list V1 through VM U1 through UJ, which is also linearly independent, since it is a basis for V1. Hence, A1 equals dot 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 all the way down to AM equals B1 equals dot 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 all the way down to BJ. All of those guys are equal to 0. So, B is linearly independent, and since it is a spanning list, it is a basis of V1 plus V2. Nice. All right, let's draw an analogy. Okay, so here's the analogy to end the day. Basically, what we're going to do is we're going to draw a comparison between some facts that are true for sets and some facts that are true for vector spaces, which are sets with some nice additional structure. The fact that you get some similarities here is kind of cool. So on the level of sets, we'll start out with finite sets. The analogy for vector spaces is finite dimensionality. So a finite dimensional vector space is basically kind of like, well, it's a finite, it's not itself necessarily a finite set. It could be, but it shares many of the nice properties of a finite set. So you could, in a finite set, count the number of elements, which we'll denote by number sign S, pound sign S. So the number of things that are in S. Okay. You can also, for a finite dimensional vector space, look at the number of things that are in a basis. Okay, this is just the number of things that are in a list that is linearly independent and spans V. For a finite set, you can take subsets S1 and S2 and look at their union, just the same way you can take subspaces V1 and V2 of a vector space and look at the sum of those subspaces. When you take the union of two subsets, you get the smallest subset that contains S1 and S2, that contains both. And similarly, when you take the sum of two subspaces, you get the smallest subspace containing both. Oh, okay, kind of cool. Dimension also works basically like inclusion-exclusion counting. When you count the number of things in the union of two subsets, you get the number of things in each, and then you subtract off the number of things that were in both because you double counted them when you counted S1 and S2. That is, if you have some things that are in both S1 and S2, then when you count how many things are in S1 and you count how many things are in S2, you've double counted some of them, so you have to get rid of the things you double counted. Basically, the exact same thing works for finite dimensional vector spaces and their subspaces. If you want to look at the dimension of the sum of two subspaces of a finite dimensional vector space, you sum their dimensions and then you subtract the dimension of their intersection, which is also a subspace. Pretty neat. And then, if, as a corollary, if the intersection of two subsets, S1 and S2, has the same number of, if the union of two subsets, S1 and S2, has the same number of elements as just S1 plus S2, well then from the previous thing, from this one right here, This says that the size of their intersection has to be 0. That is, their intersection has to be the empty set. They don't intersect at all. Similarly, if you want to go back over to the world of subspaces of a finite dimensional vector space, if you look at the dimension of v1 plus v2, the sum of those subspaces, if that is just equal to the dimension of v1 plus the dimension of v2, then from this guy right here, this means that the dimension of their intersection was 0, and there is only one subspace that has dimension 0. It is particularly just the subspace that only contains the 0 vector, the additive identity in the vector space. Huh, kind of nice. All right, and finally, if you have a disjoint union of subsets, that is, subsets that don't intersect each other at all, then the number of elements in the union of all of those subsets that are disjoint is just the sum of the number of elements in each of them. This is exactly the same kind of statement in a vector space you can make about direct sums and why direct sums are important. So a direct sum of subspaces is analogous to a disjoint union. That is, you have a direct sum only when there is no extraneous information, no repeated information, duplicates, everything. Each of the things in the direct sum is truly separate from the other pieces of the sum. Okay, this says that the dimension of v1 plus ... all the way down to vm, the dimension of the sum of these subspaces is equal to the sum of the dimension. Cool. So the number of elements in a set distributes over disjoint unions, and the dimension of subspaces or vector spaces distributes over direct sums. Pretty cool. Basically, the same thing. This is the power of dimension. This right here is why dimension is important. Having a numerical, just having like a number, an invariant number you can just associate to a vector space gives you a lot of nice, easy results. We saw that today. The reason why this particular one is so powerful and useful is it basically allows us to treat finite dimensional vector spaces kind of like finite sets in a certain way. That is, in the ways we just outlined right here. Without this, even finite dimensional vector spaces are often unmanageably large, if you want to think of it like that. Just the real numbers are a vector space over themselves as a field, then that has uncountably many elements in it, right? It is nothing like a finite set. But by using bases and the power of dimension, which gives this, invariant to the vector space, that is a number describing how many things are in any basis of the vector space, we now inherit a lot of properties of finite sets into something that is not necessarily quite finite at all. It can be indeed very, very much larger than finite. So, dimension, pretty neat. We'll do a whole lot more with it from here on out. But let's call it quits for today. See you next time.